So I was hoping that people would maybe be able to help me. I should also say that I don't know a great deal about change points. My background is in non-parametric regression. So apologies in advance if my questions are very trivial or in fact impossible. How does this work? Am I pointing the wrong way? That way. Okay, so my talk has three parts to it. I thought I should start off by at least talking about something that I knew how to do a little bit. And that is how to smooth shapes. And I've started that work, but if people would like to work on it with me, I'd be very happy to. And in particular, I'm interested in sort of mesh processing. So if you've observed a manifold at a discrete set of points, you want to try and estimate the underlying kind of manifold. And I'm going to talk about that. And what I'm going to do is I'm going to try and create a adaptive set of basis functions for the manifold using its local geometry. I'm going to decompose those coordinate functions of the points that I've observed. I'm going to threshold and I'm going to try and get back the underlying manifold. So that's a bit that I've done and I've got some very initial preliminary results for. And then, as I said, as it's a change point conference, I thought I should have some change point questions too. I don't know how to do these at all. So this is where I was hoping that people could help me. So the first one, I went to a really fascinating seminar recently. It was on social networks. And I kind of thought, well, how do people find out change points for social networks? So you can model social networks as kind of random graphs, and they're partially observed at a series of times. How could you kind of see if there's a change point in the nature of the social network? And then I used to do quite a lot of thresholding stuff for my PhD. So I was interested in how you could potentially kind of characterize varying sparsity in a sequence as well. So I'm going to start off with the stuff that I know a little bit how to do, and that's shape smoothing. So what's the problem that we're trying to solve? So let's assume that I've observed a set of points, x1 up to xn, that lie in some space R to the power m. And these observations, x1 up to xn, are noisy observations of points that lie on an unknown manifold M. You know a little bit more than the fact that they just kind of lie on an unknown manifold M. You know the neighborhoods as well. So you know the kind of connectivity between the points. And what I'd like to do is I'd like to try and estimate the underlying manifold M given the observations x1 up to xn. So here's an example. So is that the, no? Oh, I don't know how. So here's a kind of 1D manifold, and the black line is the actual curve, and I observed a series of points that you can maybe see if they're little red dots, and they're the x1 up to xn, but I know the sort of triangulation like a mesh, the way that they kind of are linked to each other. So that's a 1D manifold that I've looked at. More complicated, I might have a two-dimensional manifold, which is a statue of David. And again, I've been able to kind of form a triangulated mesh of the underlying manifold, and I'd like to be able to kind of denoise that. And importantly, you should note that that manifold has genus 1. It's got a hole in the middle of it, which makes normal kind of denoising a little bit more difficult. So how am I going to do this? Well, there are kind of ways that people kind of do this denoising previously. You can define the equivalent of Fourier series, or Fourier basis functions on the manifold, and you can kind of use those to smooth things. But the problem with Fourier basis functions is they're global functions. So maybe I kind of ideally would like to be able to kind of generate localized basis functions on my manifold. And to do that, what we're going to do is we're going to use the lifting scheme, which Matt Nunes talked about kind of earlier today. I'm going to give a little bit of a recap about that, but it was created by Wim Sweldens in 1996, and it's a way of building your own sort of wavelet kind of bases for very general kind of networks and things like that. And Martin Janssen, Guy Nason, and Bernard Silverman in 2009 sort of created kind of a lifting transform on a particular network that allows you to statistically formalize the idea of estimating functions. And we're going to use this lifting scheme to try and do some denoising. So what's the general idea that we're going to do? So we're going to assume initially that the underlying manifold M is locally smooth. And then we've observed this manifold at a series of points, And those series of points are noisy, but they still give me some idea of the local geometry of the surface, and then specifically the kind of neighborhood structure. So we know which points are close to which other points. And I can use that local neighborhood structure to try and create a set of adaptive basis functions on my manifold in such a way that if I then decompose the coordinate functions, I should hopefully get a sparse expansion. It looks a bit complicated, maybe, but I've got some illustrations that hopefully make it a little bit simpler afterwards. Okay, so that I'll briefly explain what the lifting scheme does. So assume here I've got a network of 7 points, and they're all connected to each other according to the lines. And at each node, I have a particular kind of value of my function. So I've got 7 points, and at node 1, kind of here on the left, that has value x1, x2, x3, x4, x5, x6, and x7. Okay, and what I want to try and do is I want to try and decompose x1 up to x7 into a wavelet kind of type set of coefficients that are going to be sparse. So the lifting algorithm works, well, one way it works is by lifting one of these coefficients at a time. So what I do is I'm going to pick one of these nodes, I'm going to alter the x at that particular node to a wavelet coefficient. So I'm going to start off by picking the node right in the middle that says x4, and that's going to be the coefficient that I'm going to lift. To do my lifting, I have to define a set of neighbours. So the natural way to define my set of neighbours there is just to choose the ones that are linked to it. And it has 4 neighbours, at which point I have 4 observations of what my function x is. And what I'm going to do is I'm going to try and predict what the value for xi is based upon its 4 neighbours. And I can do that in like quite a general way. And I create a prediction based upon the neighbours kind of there. And I see what the difference is between that prediction and the value that I observe at that node. And that becomes sort of my wavelet coefficient. Then what I have to do is I have to slightly adjust all of the neighbouring values, x1j, x2j, x3j, x4j, according to this particular step. And then what I've got is I've got one wavelet coefficient, and then I still have 6 x's that I need to deal with. So what I do then is I iterate that process, each time kind of updating the set of neighbours for each point, until eventually, instead of x1 up to x7, I've got 7 wavelet type coefficients, which are hopefully kind of sparse. Okay, so how does that help us in denoising manifolds? So let's suppose that I've observed a set of points, x1 up to xn, and they're just kind of, it's a one-dimensional manifold, so it's just something you could draw with a pencil on a bit of paper. And I know, kind of, I've worked my way around my shape, so I know that x1 is connected to x2, which is connected to x3 as I go around. And so I have a mesh that I can create of points. And I'm going to try and use this mesh twice in my method to denoise the manifold M. So firstly, these noisy xi's, even though they're noisy, they give me some idea of what the underlying manifold is going to be, and specifically, they tell me kind of what the neighbouring points are. So I can try and use my lifting scheme to predict the value at any kind of mesh point based upon its direct neighbours, or its neighbours that are 2 apart or 3 apart. And I can try and create that prediction so that if my manifold's smooth, then the prediction is going to be very close to the actual kind of observed value. So that will kind of give me a sparse lifted coefficient. And I can kind of keep doing that. And eventually I can decompose all my coordinate functions, x and y, and I can kind of threshold those. And hopefully what I'm going to do is I'm going to get the shape back, but with less noise on it. Okay? So as I said, at the moment, I've only done 1 dimension. But here's kind of my illustration. So here's my shape that maybe looks a little bit like a shell. And the red dots you can see a little bit more clearly are the points that I've observed. And this is really just a network where each particular point has 2 neighbours. And on the right-hand side, I've zoomed in a little bit by just arbitrarily kind of choosing one of these points that I've observed to be labelled 1, and then working my way around 2, 3, 4 as I go all the way around kind of my shape. So here, point 6 has neighbours kind of 5 and 7 in my network. Point 4 has neighbours 3 and 5 in my network. And all I've done so far in my preliminary investigation is the simplest case where I'm just going to predict the coordinate value based upon its distance to its nearest neighbour. So I'll predict the value of a function at point 5 based upon the values that I see at point 4 and point 6 according to the distance between those two things. Okay, so that's equivalent to really kind of mapping my network just to a simple interval. So I've started with point 1, and that's going to kind of, the distance here is going to sort of really tell me how far I am working my way around the shape. So point 1, I can work out the distance between point 1 and point 2, and that's just that distance there. And at point 1, the x-coordinate is about 0.01, and at x2, the x-coordinate is about 0.02. And then I can work my way from point 2 to point 3. I can see the distance in between those, and that's going to get me a little bit further along my interval, and I write down what the x-coordinate there is as well. And I can kind of continue around, working out the distance between my observed points on the network, and plotting the value of the x-coordinate on my manifold, until eventually I've kind of got a whole series of points, and I've worked my way all around my shape, and I've got back to the start. And so this is kind of what you get after you've kind of worked your way all around that particular shape. In reality, kind of these things should be mapped around to each other. So this point here is actually kind of very close to that point there. So I've got a series of two functions, the x-coordinate and the y-coordinate, and they're all now on kind of an irregular grid. And all I have to do is I have to kind of denoise that particular set of functions and put them back together, and hopefully I've got my manifold again. And I'm going to do that kind of via lifting. So as I said, I've only done very preliminary examples on a couple of shapes. So here's my example that has a circle. So I chose an underlying example that was a circle. I chose 1,000 points randomly spaced around my circle. I added some observational noise, and that gives me the plot on the left-hand side. I applied my method, and that gives me kind of the plot on the right-hand side. And this is no way simulation study, because I did it once. But that removed kind of 52% of the noise on my shape. I did a slightly more complicated shape as well, that I thought looked a little bit like a cog. That's the true shape on the left-hand side. Again, I chose 1,000 random points around that shape, added independent noise to the x direction and the y direction. That got me the red kind of set of points. And then after denoising, I got the value, I got the curve on the right-hand side. And again, not a simulation study, but it removed 48% of the noise. So that's kind of all I've really kind of done on that so far. So if people want to help me with that, I'd be very happy. There's still lots of stuff to do. So in reality, kind of 1D manifolds aren't very interesting. So I'd like to be able to try and extend it to 2-dimensional manifolds, especially kind of when you've got holes in your 2-dimensional manifold. So the genus of the shape or the manifold is going to be non-zero. That's going to be a little bit more difficult because finding the distance between points on a manifold is actually NP hard. So you might have to kind of use other kind of ways of doing your predictions. So you might maybe project onto the plane of its neighbours and the distance between the plane, and the point might be your lifting coefficient. Or alternatively, you might actually just kind of use the connectivity graph and use Dijkstra's algorithm. That might work as well. At the moment, what I'm doing is I'm thresholding each coordinate function independently, and it'd be nice to be able to threshold them jointly, and hopefully kind of maybe you could obtain rotational invariance in your denoising. As well as that, at the moment I've just done the default method of the order in which to lift my coefficients, but there might be more sensible ways in which to work your way around the shape and decide which predictions you're going to do at which point. And then also it'd be nice to maybe find credible intervals for what I think the manifold surface might be as well. How much longer have I got left? 10 minutes. Oh, great. No, I've still got more. Okay, so this is like the first bit. Okay, so I'll miss this bit out. Okay, so that was the bit of something I know hopefully a little bit about. I said I also have two questions that I know very, very little about, and I was hoping that you'd all be able to kind of help me with. I said I'm apologising in advance if they're silly. So two things that I thought might be interesting to look at change points were we have social networks, as I said, and also how you might characterise changes in sparsity of a sequence. So I don't know how much people kind of know about social networks, so I thought I'd try and give a little summary. So there are lots of kind of different ways that one could define a social network, but one way you might do it is via a random graph. So if you have a series of people, then each people would have a node. So in this case, I've got 7 people, and the nodes denote whether there's a connection between the people. So in this case, person A knows person C, but person A doesn't know person B. And it models kind of social networks, but it might also model sort of computer servers and things like that. And on any particular day, I'm going to assume that I'm going to observe some of these connections with a particular kind of probability, and the probability might depend upon not just whether they're connected or not, but also they might have latent locations in space as well, and that might be due to contact between those individuals. So it might be emails that people have maybe sent to each other, and you can count the number of emails between people. It might be whether people have met people on the street. It might be the number of server kind of queries that people have sent to each other. But in particular, you don't always exactly observe the adjacency matrix. Okay, so you're only going to see the edge between B and C some of the time. You're not always going to see it. So what people kind of do when they have social networks is they create what they call a socio matrix SI on a particular kind of day, and the jkth element of SI is equal to maybe kind of 1 if you observe contact between those two people, or it's 0 if you don't observe contact between those two people. So that's just, is there an edge or not? But you could kind of have other sampling schemes. You could maybe have SI, JK being the number of messages passed between individual J and individual K that give you kind of an idea of the strength of connection between the two people. And what I thought would be quite interesting, but I have no idea how to do it, is if you observed these random socio matrices for a kind of series of time, and you wanted to try and see if there was a change to the underlying graph. And I said I didn't even know specifically what a change point might even look like in this kind of particular instance. Do you want to always assume, for instance, that your underlying graph is fixed, and you're just kind of saying, right, I've got one graph and then I have another graph? Or do you want to maybe kind of allow some evolution of your graph, or slow evolution of your graph potentially kind of as well? I thought, in my lack of change point knowledge, that one thing you could do potentially is kind of you could look at the time series of each entry, but that's probably not going to work very well, and in reality you'd want to kind of combine information through the whole matrix. So I wasn't sure what you could do, but my suggestions in my thoughts were maybe you could kind of look at the eigen decomposition of your socio matrix SI. So when you look at the eigen vectors of your socio matrix, then the eigenvectors split up into kind of dense subsets where people are kind of connected. Alternatively, I was wondering whether you could do some sort of cumulative kind of sum thing, but on the whole kind of Frobenius norm of the matrix or something like that, maybe. Or the one thing I thought I could probably definitely do was use a hidden Markov model. So again, if people have suggestions, I think that's a kind of really interesting thing to look at. So I'll be very happy to chat to people about that. Okay, so that was the first thing that I really didn't know how to do at all. The second thing that I didn't know how to do was how to characterize sparsity in a sequence. So in my PhD, I did quite a lot of stuff to do with thresholding. It was popular then, it's probably got a little less popular now. And the problem kind of with thresholding is you suppose that you have a sequence of noisy observations xi, which are just kind of normal with mean mu I and variance 1. And you believe that the underlying mu I are in some sense sparse. And what you want to try and do is you want to estimate mu I from the observations x. So I've got two examples kind of here. So the left-hand side are the underlying mu's, and the right-hand side are the noisy observations kind of x. So in my top plot here, I've got something that's very sparse, and I've added noise to it. And in my bottom plot here, I've got something that's really quite dense, and I've added noise to it. And what I'd like to do is go from here kind of back to the left-hand side. So quite a lot of people have worked on that. And one particular approach that kind of works quite well is called E-Bayes thresh. And what you do is you place a prior on the mu, which is an atom of probability at 0, or mixture of an atom probability at 0 and a non-zero density gamma. Gamma can be a variety of forms, so it can sort of be double exponential or it can be normal. And the approach is that you first work out the likelihood of the data under that particular prior, and you choose W hat to be the marginal maximum likelihood estimator. You plug that back in to your prior, and then you estimate mu hat by the posterior median of the distribution given the observed values. Okay, so Johnson and Silverman trying to characterize the global sparsity. They suggested kind of two ways of clarifying sparsity of the sequence. So obviously the first one is just looking at the proportion of mu i's. Maybe it should be greater. Is that? No. The proportion of mu i's that aren't 0. And they also kind of said, well, you can look at the LP norm as well. And they came up with their method by bounding W above by a particular kind of value. And they also kind of bounded the marginal maximum likelihood estimated W hat below by looking at the proportion of mu i's that were larger than some critical value. And with that, they got kind of really nice results on convergence. And a little bit in my PhD, I kind of tried to generalize that because quite a lot of sequences that I think you see don't have this kind of uniform sparsity along their length. Okay, so if you look, for instance, at sort of the Affymetrix kind of chips, that generally there are sections where it's not sparse and there are sections kind of where it is sparse. If maybe you are denoising like an image of the sky, there might be sections where there's a galaxy, and so it's not going to be as sparse there as in other sections. So what I thought might be quite nice is if you could generalize this E-Bayes thresh approach by having a moving window. So instead of estimating kind of W hat over the whole set of data, you might just estimate it over a little section, and then kind of as you could kind of move left and right, and you get different estimates of W hat kind of in different sections. And I thought it'd be nice to kind of get some theory for that, and I was hopeful that maybe you could kind of use similar arguments that they did to get these results on convergence, but I didn't know at all how you might characterize the varying sparsity kind of within a sequence. So whether you could come up with some sort of norm that allowed there to be sections where it was sparse and to be sections kind of where it's quite dense. So again, if people had suggestions for that, that would be great. I know there's also kind of some work on kind of maxi sets, so trying to prove that the space of sequences kind of mu I where you get optimal convergence is kind of large. For different kind of different thresholding methods, that might be kind of like another suggestion that I thought if people wanted to look at, I'd be very happy to chat to them. Okay, that's it for my talk. Thank you very much for listening.
You've seen 3 different problems. Any comments or thoughts? No thoughts in the end of the day, I suppose, right? Well, perhaps we should discuss it later.
Oh, I think I had a...
Yeah, go ahead.
My hand up late, sorry. For the sparsity thing, with all the Bayesian wavelet shrinkage stuff, I mean, there's the parameter P in there, which is estimated by marginal maximum likelihood at the beginning.
which one, sorry?
Oh yeah, there's that there. I mean, you could maybe adapt that to a time varying thing. But there was earlier work by Donahoe and Johnston on the Stein unbiased risk estimation, which involved sparsity, and there was a related cross-validation score, which was quite similar. I always thought you could get sparsity estimates from that as well.
Okay.
Just a point.
Yeah, that'll be good to have a look at.
I think David had a comment he was going to say.
Oh, I was just going to say there is somebody in the room who's worked on change points in social networks, but she doesn't want to say anything because she's too shy. And that's how Chen, who in her thesis considered change points in minimal spanning trees, and as one application, discussed change points in telephone networks at Harvard University.
Okay, yeah, that'd be really interesting to have a look at.
I'm no way expert in social networks or in change point, but just a naive comment about social networks. I think it's really matter what changes are you looking for and what is the type of network. So the changes could be at the level of the nodes. For example, if the nodes are in the network or not, or at the level of the edges, but even then it could be qualitative. Like if someone likes someone and then the other that he doesn't like, or it could be quantitative, and it could be directed or not directed. I think the exact definition of the network that you're working on and what is your question, is it at the level of the nodes or the edges, will possibly change the model that you're going to use, and et cetera, et cetera. It's a very, very general.
Yes, no, I fully accept that. Yeah, what I've written, I don't think is even properly formalised. So yeah, you could, like you say, you could have directed edges. So you could say, so at the moment I've got my matrix being symmetric. So it could be not symmetric. You could actually kind of say, well, person J has to send person K a message, and that's not the same as person K sending person J a message. So yeah, I said this really is something that, like you said, I also don't know anything about, but I thought it was quite interesting.
Any other comments?
I've got a question actually, more for the room rather than for Tim. I mean, we've got distinct themes in weeks 2, 3, and 4, and social networking's not necessarily covered by those. But if there was interest,
It's on week 2. Actually.
oh, you're covering in week 2.
Yeah, Chen is going to talk in week 2. She's going to give a seminar on Tuesday in week 2 about change points on graphs, I believe. Yes. Yeah, change points. So yes.
But it'd be nice maybe if a subgroup could maybe form and have a kind of spin-off discussion if there's interested people on that, maybe next week.
And again, I don't know if you already know that about specific topics for week 2, 3, or 4. But again, week 2 will be about
Social and economic.
more finance,
Data.
economics,
Yeah.
econometrics. Week 3 will be about, say,
Energy and environment.
yes, and week 4 I'm responsible for some bioinformatics or some biological application. So if you're interested, I mean, just particularly local, I mean, UK participants who can just come at any time. Right. Well, thank you. Let's take